Assalamu alaikum. My name is Asad Zubair Bhatti, and right now I am going to prove this theorem that if G is an abelian group, I messed up the spellings of group. If G is an abelian group, that means it is a group that holds commutative property. Show that AB whole raised to the power n equals A power n B power n for all AB belongs to G and n belongs to the set of integers. Now, integers involve numbers, like not fractions, not decimals, not irrational, rational numbers. And they could be positive and they could be negative and they could also be zero. Now, now this is a group. G is a group. This has been defined to us. But what are the properties of a group? Closure property, associative property, inverse exists, identity element must exist. These are the four properties of a group. And what is an abelian group? Abelian means that there is a fifth property, and the fifth property is commutative property. That means AB can be equal to BA, should be equal to BA. Okay, now I have to show this. Now, given data, given data is that G is a group, is an abelian group. This implies AB equals BA. To prove AB raised to power n equals A power n B power n for all AB belonging to G and n belongs to the set of integers. Okay, now we will discuss the three possible cases in this scenario, that n could be a positive number, n could be a negative number, and n could be equals to 0. We will discuss three possible scenarios slash cases. It looks cool when we use the word scenario. Case 1, when n is greater than 0, or n is a positive number. Okay, it's not equals to 0 right now. I shall name this equation as 1. Okay, this given equation. Now for this scenario, we will prove, this is a general case by the way, this could be 2, this could be 3. It usually comes in different questions in different sorts. Like n could be any number, but this is a general proof. Case 1, when n is greater than 0, we will prove 1 by the help of mathematical induction. Now there are three rules to mathematical induction. First is we have to see if the result is true for n equals to 1. First step is we have to check whether the result holds true for n equals to 1. Second step is we have to suppose that n equals to k and the result will hold true. We have to suppose that if we put n equals to k, any random number, then the result will hold true. And then we will again have to prove step number 3. We have to check now if does the result hold true for n equals to k plus 1. So step 1, let n equals to 1. We have to check whether the results will hold true for n equals to 1. And our equation was ab raised to power n equals to a power n b power n. And we could say ab whole raised to power 1 equals to a power 1 b power 1 if we write this as ab equals to ab. Okay, LHS equals to RHS, the most famous term in mathematics. The result holds true for n equals to 1. Step 2. Let the result be true for n equals to k. Now we suppose that yes, the result will hold for n equals to k. So ab raised to the power k equals to a power k b power k. We name this as equation number 2 for all a b belonging to the group G and k should be greater than 0 and k belongs to the set of integers. Okay. Okay, I'll just move to the next page. Step 3. Prove the result for n equals k plus 1. So we have ab raised to the power n equals to a raised to the power n b raised to the power n. ab raised to the power k plus 1 equals to a raised to the power k plus 1 b raised to the power k plus 1. Now we will prove if the result holds true for this. We can write this as ab raised to the power k multiplied by ab. Why can we write this? Because if the bases are same, AB and AB are the bases. They are the same bases. Their powers shall add up. The power of this AB right there is K, and the power of this AB is 1. And their powers add up to become AB whole raised to the power K plus 1. Cool? Okay. Now we will only discuss the left hand side. Okay, we just write this down. Okay, we will only discuss the left hand side, which is this. Now AB whole raised to the power k, we supposed that the result does hold true. Therefore, from equation number 2, we can replace AB whole raised to the power k by A raised to the power k, B raised to the power k. So we can replace this by A raised to the power k, B raised to the power k, AB. And we haven't touched anything about the right hand side. We are going to convert this into the right hand side. The reason is using equation 2. Now, A raised to the power k, B raised to the power k, A, B equals to A raised to the power k plus 1, B raised to the power k plus 1. Associative property. Why can we use associative property since G is a group? This implies A raised to the power k, A, B raised to the power k, B equals right hand side. What did I do? I just shift this around. Can I do that? Yes. Given statement was G is an abelian group because G is abelian, hence commutative property holds. This implies a raised to power k times a, b raised to power b k times b equals a raised to power k plus 1, b raised to power k plus 1. Reason: associative property. And we can write this as a raised to power k plus 1, b raised to power k plus 1 equals to a raised to power k plus 1, b raised to power k plus 1. Cool. LHS equals RHS. Now, the result did hold true for k plus 1. Therefore, the result will hold true for n. Since result holds true for k plus 1, n equals k plus 1, by mathematical induction, this whole thing was mathematical induction. Result holds true for equation 1. For equation 1 only when n is positive and n belongs to the group of integers. Now the second case. When n equals 0. So left hand side is ab whole raised to the power n. We can write this as ab whole raised to the power 0. And okay, whole raised to the power 0. In group theory, what is the identity element? I mean, ab raised to the power 0 will lead you to the identity element. Why? Because ab is power 1 minus 1 equals to ab whole inverse. ab belong to the group G. Why can I do this? By the way, I'm writing this down. Since AB belong to the group G, therefore their product or whatever their composition may be also belongs in G. And if this belongs in G, then AB must have an inverse. Therefore, we can write this as E, the identity element. Now, identity element, no matter how many times you apply the composition on it, it will give the same result. The identity, like 0 plus 0 plus 0. Under addition, this will always result in 0, and 0 is the identity element. In multiplication case, in the case of multiplication, 1 is the identity element. So 1 times 1 times 1 times 1 times infinity times 1, that will always result in 1. So in general, while speaking generally, um, in the group theory, if E is the identity element and whatever the composition may be, how many times if you use that composition on E, that will always result in E. Therefore, we can write this as E dot E, right? And we can also write this as A inverse of A, B inverse of B, because A inverse A equals to E and B inverse B also equals E. A inverse AB, B AB inverse B, associative property. Now, A inverse B inverse A times B, because G is a billion. Therefore, commutative property holds. This reason is enough, by the way. If you write G is a billion, you don't have to write commutative property holds, because if you write G is a billion, then it is obviously stated that G holds commutative property. This equals A inverse B inverse A B, because I shifted the brackets, that's it. Associative property. Now, this results in B A A B. Oh, sorry, B A whole inverse, because um, A inverse B inverse results in BA. That is another theorem. It expands in the opposite direction. Equals AB whole inverse AB, because G is an abelian group. Now AB inverse times AB, the bases are same, so the powers will add up. Here we are. I kind of messed it up over here actually. Wait a minute. Okay, sorry, erase these last two steps. From here, we're going to talk about A inverse, B inverse, AB. Okay, we are going to continue from here. I kind of did an error. We open the brackets like this. We can do that because it is an associative property of the groups. And we can write this as A inverse A, B inverse B, right? And we can write this as A inverse A, B inverse B. The reason for the above step is G is an abelian group. So commutative property holds. You can shift things around. Associative property. Now, A inverse A, the bases are same, so the powers will add up. Similarly for this thing, you can write this as A dot A times 0, B times 0. Cool. Now, we said that n equals 0, but n equals to 0. Therefore, A raised to the power n, B raised to the power n. And this is our right hand side. That is what we had to prove. We had to prove that AB whole raised to the power n equals A raised to the power n, B raised to the power n for n equals to 0 in this case. And that's what we did. Now case 3, which is when n is a negative number. Or we can write this as n equals to minus m. Like m is the positive number times minus 1. You can write this as like that. Therefore, AB, we will only talk about left hand side, and then we will convert it into the right hand side and prove that they are equal. AB whole raised to the power m minus m. This also means AB whole raised to the power minus 1 multiplied by m. Nothing wrong in that. And we can also write AB whole raised to the power minus 1 times m, because it is the rule of integers that x, y, a, sorry, x power a whole raised to the power b equals x power a times b. That was the rule. So we will expand this inside function, and AB whole inverse, according to a theorem, it expands as B inverse A inverse, because AB whole inverse equals B inverse times A inverse equals A inverse B inverse whole power m, because commutative property. And we can also write this a raised to power minus m, b raised to power minus m. We just multiplied m with each number. It is also another rule of indices and whatnot. And we set n equals minus m. So we can replace this minus m with this n. So this equals a power n, b power n, because n equals minus m. And this is equals to our right hand side. So LHS is equals to RHS. Proved. Now all the cases have been proved, and in the three different scenarios we proved that AB whole raised to the power m should be equals to a power n, b power n. And now the question which usually arises in students' minds in the group theory is that why are we doing these obvious steps, like these steps, I mean, we know that AB whole raised to power minus m should be equals to B, all this we know that, but in group theory, why? Because group theory is the basic of mathematics right there. It's the basic of numbers. It defines like everything has been. You can say that all the number theories evolve from group theory. Group theory defines logic with numbers. Like a property can hold for 2, 4, 6, may also hold for 4, 3, 5, 7. It may not. All of these things are defined by group theory. And so when you have to prove something, you cannot use what you have to prove in the proof itself. You have to go through another route. So when you are proving the basic fundamentals of mathematics, you are not going to say that, oh, we know that. I mean, come on, we can skip all these steps. We skip all these steps. We have to use all of these steps and define them as it is. Imagine that you are explaining to somebody who has never even heard of a number in his life. That's how you are going to explain group theory to someone else. You have to give reason for literally every single thing, even including 1 minus 1. That's how group theory works. So thank you very much.